Here's our updated system palette. So we first define the pallet's generic arguments, account ID, block number, and nonce, and reuse them inside the fields. Like block number is obviously the block number type, and the nonce is a B-tree map mapping from account ID to nonce. Now inside the implement block, we define the generics and the constraints of the types, like account ID is bounded by order and clone, a block number by other traits, and nonce by others. I would say we first take a look at the solution, and at the end I will walk you through why we need these traits and what kind of issues might run into. So we need to update every function here which had previously explicit number. So everywhere where we had either a 1 or a 0, now we need to replace with the generic type and the function. So for example, we had previously here a 0. Now we access block number 0. Same applies for this line of code. We had here previously 1. Now we access block number 1. Here we had to replace the explicit value with nonce. Here we access nonce 0. Here nonce 1. Finally, inside our tests, we access a super palette and define here with the turbofish notation again, and make it explicit what kind of type it is of a system palette, namely string U32, U32. We can move on to main RS, where we move some of the types that we had previously there to the mods types. Here we've got now block number and nonce, both defined as U32. Inside our runtime, we need to define explicitly what kind of system palette we expect it to be. In this case, we can see that we got the system palette and access the types, account ID, and types block number, and types nonce. Now, into what kind of problems you might have run into? What kind of questions you might have is, why do we, for example, need add assign? Well, at this line of code, we use plus equal, which is we take the block number, add 1, and reassign it back. And this is, to perform this operation, you need the add assign trait. Next question you might have is, why do we use core OPS and add assign from here? There's another add assign you might have run into inside std ops add assign. Why don't we use that instead? It would actually work as well. So I've done it. There are no compiler warnings. But here we use the std stuff. And originally we don't want to use std. Inside a blockchain environment, you don't want to assume anything about where this code runs. So normally we prefer to not use std in this example as well, since it should align with a real blockchain environment. Another question you might have is, why don't we need the add trait? Like here, we actually add two nonces together. So why don't we need the add trait? Can we just assume add is there? No, actually not. But the add trait is implicitly already included. If we take a look at the 0 trait, we can see that the 0 trait requires to have add trait as well. So it's a super trait of 0. And because we we constrain nonce to implement 0, we implicitly say, okay, there's the add trait as well. Same applies for the block number. Finally, why do we need the copy trait? Well, for the block number, because we here return self block number, and we can't just move the ownership of the block number to something external. So it's implicitly being cloned, like here. This would be the same, but it's a little bit prettier to just say, okay, block number, and then move it away, clone it implicitly. And for the nonce, this is happening at this line. So what I've highlighted right now here. This is a reference, what I highlighted. So we get a reference and then dereference it through the dereference operator. But then it is implicitly being cloned and moved to nonce. So we receive here a nonce which is owned inside this nonce variable. Then we can go ahead and add, for example, 1 to it and create a new nonce whatsoever. I hope now all your questions regarding these traits have been clarified. We will now move on to the next lesson.